We return now to combinations, and combinations are strikingly different from permutations, because permutations had to take into consideration the order of the elements present. Combinations, the order is irrelevant. In other words, when we have a combination, we're simply choosing a bundle of objects. The order of that bundle is of no consequence to the mathematics, but if we were dealing with permutations, then the order would be extremely important. So just go back to permutations for a quick moment in terms of horses. The order in which they finish is extremely important, first, second and third, so we can distribute the prizes accordingly. With a combination, that's not the case. With a combination, we're simply choosing a smaller bundle out of a larger original set. So combinations, first and foremost, as we said, the order does not matter. So they're treated as a group. So whatever you select, you're treating as a group. In general, the number of groups of R that can be chosen from a population of n is called NCR. Now it's written this way here. You'll see that in your textbooks, NCR. And again, the way to think of it is, out of n objects, I want to choose R. So for example, if you had 10 sweets and your granny told you to take 3, it would be 10, out of the 10, choose 3. And the order in which you choose them doesn't matter, because you'll still have 3 sweets at the end. So that NCR is what we're going to use, and it's on your calculator, and I'll show you where that button is in a few moments. If you go over the division button, you'll see it there, NCR. So again, it's a second function, or what we call a shift function. So you press shift NCR after you put in the first number. So for example, go back to Granny Sweets. Granny tells you to take 3 out of a bag of 10. It would be 10 C3. Out of 10, choose 3. On your calculator, you would type 10 shift division 3, and that will give you the answer to that one. So again, we go back to something which we brought into permutations, the words and the word or. They're very loaded when it comes to mathematics, because we did say already that when you have an and an or, they represent mathematical functions. The word and represents multiplication. The word or represents addition. So be on the watch out for those two words very, very carefully when you're reading questions. So take, for example, 9C6. 9C6 means that out of 9, you choose 6. Now, go back to our factorial. Factorial was 9 factorial, which meant 9 all the way back as far as 1 through multiplication. So 9 by 8 by 7 by 6 by 4 by 3 by 2 by 1. 9C6 means that you start at 9, but you go back 6 numbers. So 9 by 8 by 7 by 6 by 5 by 4. And on the bottom then, we start at 1 and we move up 6 digits. So 1 by 2 by 3 by 4 by 5 by 6. Okay, so that's another way of calculating 9C6. It's the longest way to do it. You'll be glad to know you won't be doing that because you'll be using your calculator, but just to show you where it comes from. So out of 9, choose 6. That means start at 9 and go back 6 digits, 6 what we could say natural numbers, and then on the bottom start at 1 and go up 6 digits. But you'll notice straight away that if you take 9 by 8 by 7 by 6 by 5 by 4 over 1 by 2 by 3 by 4 by 5 by 6, there's cancellation. 6's cancel, the 5's cancel, and the 4's cancel, which leave you with 9 by 8 by 7 over 1 by 2 by 3, which can be written instead as 9C3. And 9C3 means start at 9 and go back 3 digits, so 9, 8 and 7. On the bottom, start at 1 and go up 3 digits, 1, 2 and 3. You get exactly the same answer because of the cancellation here. The answer of 84 is exactly the same as 9C6. So there's a rule here, the twin rule, and here it is. If the number of objects that you're choosing is greater than half of the original group that you're choosing from, well then we can subtract the bottom number from the top number and we can simplify this combination. So 9C6, 6 is greater than half of 9, therefore 6 from 9 is 3, and that gives me 9C3. Another example would be, say, 12C7. If I was asked to do 12C7, what would I do? Well, I wouldn't certainly do 12C7 because 7 is over half of 12, so therefore I would simply put down 12C5. Doesn't seem like much of a difference, but it is easier to calculate should you forget your calculator when you're doing these things, which obviously you won't, but just in case you did. Okay, so therefore, when we want to simplify NCR, we simply take it as n over the difference between the two, only if R is greater, or sorry, is greater than half of n. Okay, and that's a rule that we have down here. So you subtract r from n only when r is greater than a half of n. Now, if I gave you 12c3, for example, you'd leave it alone. 12c6, that's in the middle. 12c7, as we said already, would become 12c5. 12c9 would become 12c3, and so on. Just, it's a little simplification on the way, makes things a little easier as we do these questions. So, before we move into the questions themselves, here's two things that you should be very, very familiar with. First of all, you should be very familiar with dice. Now, dice is plural. Just clear this up before we move on. So you've got two dice. One of them is a die, which gives interesting consideration to the word mice. If mice is plural, does that mean if you only have one, you have a my? Well, don't know. Have to look it up and see. I was never any good at English, I keep telling you that, so therefore I don't care. I just care about maths. So this is a dice. These are dice, and this is a die. D-I-E. So you'll hear me talk about die, and you'll see the questions will refer to a die when they want you to use one, and it'll be dice when they want you to use two or more. Also, what kind of astounds me these days is that a lot of people are not familiar with what we call a standard pack of playing cards. So I've put them here for you so that you can see them. Nobody has any excuses going forward. There are 4 what we call suits. We've got clubs, hearts, spades, and diamonds. Okay. In each suit, you have an ace, all the way up as far as a king. So that sometimes stands as number 1. So 1, 2, 3, all the way up as far as 10, 11, 12, and 13. So there are 13 cards in a suit. There are 4 suits in a pack, which means there are 52 cards in a standard playing pack. Now you might say, where are the jokers? We don't involve the jokers. Yeah, jokers are left out. Maths is a serious subject. No time for jokers. So here it's from the ace to the king of a given suit. And then because there are 4 suits, we have 4 13s, which is 52. Now there's another breakdown. Look at it very carefully. One more breakdown. Half of them are black and half of them are red. So keep that in mind. The club suit is black, the spade suit is black, the heart suit is red, the diamond suit is red. Okay, so I want you to visualize that. If you've never played with a pack of cards before, I want you to visualize that, or even better still, now that you've got plenty of time off, go out and buy yourself a pack of cards and start playing cards with the rest of the family. Play poker, not for money, play it for maths. Okay, so worked example. 12 points are drawn on a circle. Question 1. How many different chords could be drawn between these points? Now, you have to understand what a chord is. A chord is a line that joins any 2 points on the circumference of a circle without going through the middle. Because if it went through the middle, it would be a diameter. Okay, but still, we could still call a diameter a chord. But usually when we're dealing with chords in geometry, we talk about the chord that runs from one side of the circumference to the other side without going through the center. But here, we're going to take all possibilities. Okay, so how many different chords could be drawn between these points? So, if a chord contains 2 points, and there are 12 to choose from, can you see it? 12C2. That's it. 12C2. And 12C2 is already in its most simplest form. Now you can do this in your head, because really 12C2 means start at 12 and go back 2 digits. Start at 1 and go up there. So therefore that goes in there 6 times, and 6 11s, 66. See? So it's lovely to be able to use these combinations in terms of fractions if you want to do cancellation. Next question says, how many different triangles may be drawn by connecting the points? Now in this case here, we've got 12 points. In order to create a triangle, you connect any 3. So triangle would be something like that, from there to there, or you might have one going from there to there to there, and so on. Okay, so that means, let me just get rid of that, give me some space. That means that if we want to take the 12 original points, we're going to choose any 3 to form a triangle. So in this case again, 12 by 11 by 10 over 1 by 2 by 3. Starting at 12 going back 3 digits, starting at 1 going up 3 digits. Then do the cancellation. 3 into 3 goes once, into 12 goes 4 times. 2 into 2 goes once, into 10 goes twice. And then you've got your answer. 4 2s are 8, 8 11s are 88 different ways. Okay, NCR itself, that's what's on your calculator. We normally use it as NCR in your books like that, NCR, and it has 2 brackets. I don't really use the 2 brackets, I use 1. You'll see me write this when I'm dealing with it, yeah? Out of N, choose R. I don't finish off the brackets. In your maths book, the brackets are at the front and at the end of the N and the R. So NCR is used when there is one experiment with no restrictions. So let's move on. If there are two experiments taking place, go back to your permutations. It'll be the first one and the second one, the first one or the second one. So E1 multiplied by E2 if it's and E1 plus E2 if it's or. And I have those rules written down for you here. So if it's one event or a second event, you take NCR for the first event, and then you add it to NCR for the second event. But if it is one event and a second event, so you've got to read your questions carefully, then it will be NCR for experiment 1 multiplied by NCR for experiment 2. And that's what's going to get you through the rest of this section. Just keeping those rules in mind. NCR, out of N choose R, and then if it's two events and it's one or the other, you add the results. If it's one and the other, you multiply the results. So when we place restrictions on combinations, we simply treat each event separately. So when you're putting restrictions on, say for example, a question which we'll do in a few moments, something like there are 5 managers and 4 workers, say 5 managers and 4 workers. Out of how many groups can you make of 4 people if everybody's to be involved? So it would be 9 C4. But then they might say something to you like, well, there has to be more managers than workers, or you're only allowed to have 1 manager. So they start to put restrictions on your questions. In situations like that, my advice would be take each event separately. Work out each event separately and then ask yourself, what's the connecting word? Is it and or is it or? So let's take an example here. How many boards of 5 members can be arranged from 4 managers and 5 workers? Now we've got managers and we've got workers. We've got 4 managers, we've got 5 workers. Okay. There are no restrictions in part 1. So I want to get 5 members. So if I take that together, that means that there are 9 people altogether. And out of those 9, I want to choose any 5 because I want to make a board of 5. So 9C5, better known as 9C4, because of the cancellation, 5 is greater than half of 9, so take it away, NC4, and then work it out. That means 9 by 8 by 7 by 6 over 1 by 2 by 3 by 4. Now I'm doing the long way at the moment because I want you to see how the multiplication works and how the simplification works through division, and then I'll go on to the calculator later on. I won't be doing this at all. So 4 into 4 goes once, 4 into 8 goes twice, 3 into 3 goes once, 3 into 9 goes 3 times, 2 into 2 goes once, 2 into 6 goes 3 times. So what do we end up with? We end up with 3 by 2 by 3, which is 18, over nothing on the bottom, everything's gone. 1 is left on its own, so it's 18 over 1, which is 18. And if you tap into your calculator 9C4 or 9C5, you'll get exactly the same answer. Okay, if there must be more workers than managers. Now here's where we've got to slow down, okay? We've got 4 managers and we've got 5 workers, but we want more workers than managers. Doesn't that mean that we could have 5 workers and no managers, or 4 workers and 1 manager, or 3 workers and 2 managers? Now if we went to 3 workers and 2 managers, that would be too many workers. So we have to have more workers than managers. So if we went from 2 to 3, I should say, we'd have too many managers. So we can't have that. So therefore, listen again. We could have 5 workers and, do you hear it? No managers. Or we could have 4 workers and 1 manager. Or we could have 3 workers and 2 managers. So let's try that out. 5C5 for the first one, and no managers, so 4C0. Okay, now that's easy to work out. And again, 5C5 is 1, 4C0 is 1, so that's one way. You can check those in your calculator as well. 5C5 is 1 and 4C0 is 1. Okay, next one. Out of the 5 workers, I want to choose 4. So 5, choose any 4 workers. And along with that, out of the 4 managers, I want to choose 1. So 5C4, do your subtraction. That's the same as 5C1, which is 5. And, okay, 4C1, which is 4. So that gives me 20. And then I want to have, out of the workers, out of the 5 workers, I want to need 3. So 5C3, and out of the managers, out of the 4 managers, I want to choose 2. So 5C3, which is the same as 5C2. Let's just do that over here. What's 5C2? It's 5 by 4 over 1 by 2. What does that give me? 2 into 2 goes once, 2 into 4 goes twice. That gives me 5 twos. That gives me 10. Multiplied by 4C2, which is 4 times 3 over 1 times 2. What does that work out as? Well, do your cancellation, that's 6, which is 60. So therefore, there's one way if I have 5 workers and no managers, there's 20 ways if I have 4 workers and 1 manager, and there are 60 ways if I have 3 workers and 2 managers, giving me a total of 81 different ways. Okay, and then the last one, there's only allowed to be 1 worker. So again, if there's only allowed to be 1 worker, take care of that first. Out of the 5 workers, I'm only allowed to choose 1. And along with that 1, out of the 4 managers, I must choose all 4. See that? So therefore, what does that give me? 5C1 is 5. 4C4 from your calculator is the same as 4C0, which is 1. And that gives you 5 times 1 is 5 different ways. And again, think about it. If you pick 1 worker and you want to pair them off with any of the 4 managers, well, that's going to be what? That's going to be 4 times, or 5 times 1, which is 5. So 1 worker, there it is, there's the 1 out of 5. Then we have to choose all 4 managers together to make up a team of 5. So therefore, there's 5 possibilities here. There's only one way to choose all 4 managers, that's to put them all into one group. So therefore, all managers with worker 1, or all managers with worker 2, or all managers with worker 3, etc. That's where you get your 5 from. So it's a very nice way to do that thing very quickly. Okay, so it said back there, simple diagrams are a great help in solving these. As I'm doing at the moment, just draw out your combinations. Take every event separately. Okay, next one. A standard pack of cards contains 52 playing cards. How many different poker hands can be dealt to a player? Now, what's a poker hand? A poker hand is 5 cards. Yeah? So therefore, we've got a standard pack of 52, out of which we want to choose 5. So this here would be 52C5. And 52C5 works out as, and I've done this earlier on the calculator, 2,598,960. So that's what you get when you deal with 5C2. It's quite a big number. Next one. How many hands must include the ace of spades? Now, if the ace of spades is already in, well then that's 1 card less we have to worry about. So what that does is reduces the number of cards down to 51, out of which to make up your poker hand you've got to choose the remaining 4. So 51C4, and again I've done this on the calculator, it comes out as 249,900. Okay. Number 3, how many hands do not include the ace of spades? Now, we had this before when we were dealing with permutations. You notice anything? How many hands include the ace of spades? How many hands do not include the ace of spades? These are opposites. If I was to add these two together, I would get the total number of poker hands available. So therefore, if there's 249,900 that include the ace of spades, surely the difference between these two must be the hands that don't have the ace of spades. So when you take 249,900 away from 2,598,960, you get 2,349,060. Okay. Part 4. How many hands contain all 4 aces? Okay, so all 4 aces pushed to the side. How many does that leave me with? Doesn't that leave me with 48 cards? And out of that 48, I'm only allowed to choose 1 to get my poker hand, because a poker hand has 5 cards. And 48C1 is 48. Okay, now I want to do the last part. And I'm just going to make a little bit of space here, because I want to do the last part. It takes a little bit of time to do it up here, in this section. How many hands contain exactly 3 aces? Now, which 3 aces? We don't know. So therefore it doesn't specify which 3 aces. So the very first thing I've got to remember is that I'm going to be picking aces with non-aces. Okay, so you'll have aces and you'll have non-aces. Do you hear that? Aces and non-aces. That's multiplication. So therefore, out of the 4 aces, I can choose any 3. Multiplied by what? Well, what's left? Out of the 4 aces, I'm allowed to choose 3. Doesn't that leave 48 cards? Out of which I must pick another 2. See? So there's the total pack, 52. There's the hand of poker, 5. So it's 4C3 for the aces, multiplied by 48C2 for the non-aces. And that's going to give me, if I do that very quickly, 4C3, obviously the same as 4C1, which is 4. And then 48C2, I'm going to do that on the calculator, is 1,128. So when we multiply those together, we get 4,512 different ways, or different hands, as we should say when we're dealing with poker. Okay, so I want to take a look at this. Now, equations involving n factorial and the combination function. We've already kind of looked at this when we were dealing with factorials previously. We do know that if nc1 is out of n choose 1, well then that's just going to be n. There's only one way to choose 1 out of n number, and that's n ways. If Granny has 10 sweets and Granny says take 1, there are 10 possible sweets you can choose from, but you're only choosing 1. So therefore 10c1 would be 10. Yeah. So in this case, nc1, in fact any number c1 is going to be n. nc2 is n multiplied by the number before it over 1 by 2. nc3 is n by the 2 numbers before it divided by 1 by 2 by 3. Okay, so again, just keep that in mind when we're dealing with n's. And likewise, as we said earlier, if you have n plus 1 factorial and you divide it by n factorial, don't forget, all smaller factorials are in the larger ones. So that n factorial is in there. In fact, n plus 1 factorial can be written down as n plus 1 times n factorial. These two then will cancel, and you'll end up with n plus 1. So just keep that back in your head as we go into these questions in relation to the equations. So let's take an example. Solve the following. nc2 equals 36. n is an element of natural numbers. Now take notice of the fact that they're putting a condition on your question. Your answer can only be from natural numbers. What does it mean? It means nc2 is n multiplied by the number before it, n minus 1, all over 1 by 2, and that's equal to 36. So what does that do? Well, that gives me n squared minus n is equal to 2 36's, 72, which gives me n squared minus n minus 72 is equal to 0. It gives me a quadratic equation. So we're back to junior cert maths. Open your brackets, n and n. We're going to have definitely 9/8 or 72. And I want minus 1, so that's minus n plus 8. So n is equal to 9, or n is equal to minus 8. Are both answers acceptable? Go back, there's a condition on your question. The answer you get must be an element of natural numbers. Reject the minus 8 and choose the n. So your answer there will be 9. Next one. n plus 1 over 2, sorry, n plus 1 c2 equals 10 times nc1. Okay, n plus 1 c2, what's that? That's n plus 1 multiplied by the number before it, n, all over 1 times 2 is equal to, now nc1, remember I told you, if you're only choosing one object out of n, well then there's n number of ways to do that. So that becomes 10 times n. What's my quadratic equation here? N squared plus n equals 20n. I hope you've got that. So you multiply these two out. N squared plus n equals 2, clear the fraction, 20n. You're multiplying both sides by 2. That gives me n squared plus n minus 20n is equal to 0. So n squared minus 19n is equal to 0. Again, back to junior cert maths. Take out the n. n minus 19 is equal to 0. n is equal to 0. Or n is equal to 19. And again, look, reject the 0 because it's natural numbers. Remember, we said this in 5th year, natural numbers don't contain 0. If they wanted to contain 0, they'd have a little 0 down here, which is not the case in this question. Okay, so solve the following. n C2 equals 36. Do we have that already? Yeah, there's the answers. Yeah, just to make sure that I'm right. So I'm checking myself. Good. Didn't realize I gave you the answers to that. That's fine. Accept 9, reject -8. And then the second one, as we said already, you accept 19 but not 0 because n is an element of n. Now, let's take a look at these questions here, these exam questions. I'm going to leave these here for you to do. I'm going to leave the question 3, security code. I'm going to ask you to pause now. I'm going to ask you to do both of these questions and then come back to me when you have them finished. So you can pause this video now. Okay, so well done. Now, let's take a security code consists of 6 digits chosen at random from digits 0 to 9. The code may begin with 0 and digits may be repeated. For example, 071737 is a valid code. How many of the possible codes will end with a 0? So here's what we have, the fundamental principle of counting, right back to our permutations. So we have 1, 2, 3, 4, 5, 6 boxes. Okay, so I'll just take 6 boxes along here. 1, 2, 3, 4, 5, and 6. They have to end with 0. So it says a security code consists of 6 digits chosen at random from the digits 0 to 9. The code may begin with 0 and digits may be repeated. That's extremely important. So if they're to end in 0, well, obviously only one digit can go in there. But all the digits are available for all the other places. So that's 10, 10, 10, 10, and 10. And again, the word "and" is between them all. So the first digit is between 0 and 9, the last digit between 0 and 9, second digit between 0 and 9, next one between 0 and 9, so on and so on. But the last one has to be just 0. So in that case, we've got 1, 2, 3, 4, 5. 1 with 5 zeros. That becomes 100,000 codes. Find how many of the possible codes will contain the digits 2018 together and in this order. Now you take the 2018 together. Okay, so therefore that's going to be 1, and it's not going to be 4 factorial because in that case we're not moving these round. So that's going to be 1 space. So that's 4 digits gone. Then I have, I need to say 7, 1, 2, 3, 4, 5, 6. So there's only 2 spaces left. Okay, so if the 2018 are gone in here, that's 1 place for them. What have we got left? We have 10 digits for here, and we have 10 digits for here. Okay, now just be careful, because the 2018 can also take any one of these 3 positions. So that's the 2018, but that could be in 2nd place, or it could be in 3rd place. So therefore, 10 tens are 100, but 100 times 3 is equal to 300. See that? As you can move this thing around the place. So because the 2018 are together in this order, we treat that just as 1 block. That's it. So there's only 1 possibility of 2018, but yet that can move into 2nd place or 3rd place, and the 10s can move into 1st place or into middle place or last place. So they can all move around. So you get the answer of 300. Find A, B, C, and D if n plus 3 factorial times n plus 2 factorial over n plus 1 factorial over times n plus 1 factorial is equal to. Okay, so in other words, what they're asking to do here is work with these factorials. What does n plus 3 factorial mean? N plus 3 factorial means n plus 3 multiplied by every other natural number below it. Now, n plus 1 factorial is in there, so keep that in mind. So n plus 3 factorial, if I was to divide that by n plus 1 factorial, will give me n plus 3 times n plus 2. Okay, and if I was to divide n plus 1 factorial into n plus 2 factorial, I would simply get n plus 2. So all I've got to do here is just multiply these out. So let's multiply out the first 2. We get n squared plus 2n plus 3n plus 6, which is n squared plus 5n plus 6. And we now want to multiply that by n plus 2 to get our cubic equation. That'll give me n cubed plus 5n squared plus 6n plus 2n squared plus 10n plus 12, and then just tidy it up. N cubed, 5n squared and 2n squared, that's 7n squared, 6n and 10n, that's 16n and plus 12. So down here, what's A? A is 1, B is 7, C is 16 and D is 12. Yep, factorials are that easy. Okay, I'm going to leave you now with these questions here from book 2. I want you to turn to page 53 and page 54 and do the following questions, and tomorrow I will come back with the solutions. If you have any difficulties, please email me the questions that you have a difficulty on and I'll get the solutions to you.